Okay, I think we're ready to get started here. So hopefully everybody can see the presentation. So I want to talk a little bit about our digital voltage regulator products and our DECS product lines in particular. This presentation is obviously about our voltage regulators. Our DECS product line goes from our DECS 150 voltage regulator all the way to our full static excitation system, such as our DECS 2100s. For the purpose of this presentation, I'll be talking about our voltage regulator lines, not necessarily the static excitation systems, but a lot of the principles apply across all of our products. So I'll go ahead and get started. To start off, I just want to discuss what a voltage regulator is. So the whole purpose of a voltage regulator is to regulate the generator voltage. So it's looking at the output of the generator at its terminals, and the voltage regulator looks at where its set point is versus what the output of the generator is and makes corrections. And it does this by applying a DC flux to the field of that particular machine. By increasing the amount of excitation to the generator field, we can increase the output of the generator or the voltage output. So I'm going to start out with a block diagram here of an analog voltage regulator, and then we'll move on to a digital. But I like to start with the analog just to see how things work. It breaks things down a little bit better. So overall, again, the voltage regulator is going to sense the output of the generator. So you can see at A here, we're looking at the output of the generator, and then we're going to compare it against the reference. So that's D and C. So A gets basically stepped down to a lower voltage signal within circuitry, and that's here at B, and it goes into this error detection scheme, and it compares this level of set point against our set point, our reference set point. So this is going to be our base set point. So, and if in case, let's just say this was a 480 volt machine, we would have the set point set at 480 volts. But if our user wanted to make minor adjustments, we could also have this external adjustment or this voltage adjust at D. In this case, it's a variable resistor. It could be a DC offset signal from another device, but it's a way to adjust the set point overall. What happens is the sensing input gets compared to the references, the sum of the references, be that external adjust and the reference point, so D and C, and we create some type of error signal. Throughout circuitry, we take that error signal and we amplify it. And that amplified error signal then gets put into the output circuit. So the output circuit takes the power output at these terminals 3 and 4 and feeds it into our power control. And then we use the output of our firing circuit. So circuitry internal is going to put the DC output into the field through terminals F plus and F minus. So it's going to create flux on the rotor, increase or decrease the amount of flux on the rotor, and increase or decrease the amount of voltage out of the machine. And then on top of all this, we also have the stability network in here. So we're going to basically dampen through some circuitry to make sure the output is nice and stable and the voltage isn't hunting around and such. So that's kind of the output, not kind of, it is the output or the block diagram of an analog voltage regulator. So we're here to talk about digital voltage regulators. So digital voltage regulator block diagram, this is kind of simplified, but it's a very similar approach to what an analog voltage regulator does, with a few exceptions. So again, we're looking at the output of the generator, and we're going to pull this into this A to D converter. So there's some scaling circuitry. So we're taking an analog signal now, and since we're working with a microprocessor, we're changing that analog signal into ones and zeros, or a digital signal. So that digital signal is going to tell our summing point, very similar to that summing point of the analog voltage regulator, what the output of the generator is. And just like the analog regulator, we've got a reference input. That is our set point. So it's going to compare the set point to the output of the generator terminals. And then we're going to go through our digital controller where the voltage regulator is going to work its magic and determine what needs to happen internally. And then we go back and we're going to take that digital signal. So this is like that firing circuit part. We take that digital signal and we turn it back into an analog output, or through our power stage, we're going to turn that into DC that's going to be put on into the exciter field in the case of a voltage regulator. We're going to Just like an analog voltage regulator, we've got that DC voltage. As we raise it, we're going to increase or decrease the output of that generator. So with that, I brought up a point there of power stages. So the voltage regulator is monitoring the output of the generator, very much like the cruise control on your car does with speed, except we're doing it with generator voltage. But the power stage is what's actually doing the work. So we're going to take that AC signal that's being fed into the voltage regulator and turn it into DC and use that to drive the flux on that rotor, or flux in the field, the magnetism in the field, higher or lower to control our generator voltage. So at a high level, there's two different ways that we do this. We take that AC signal and we use silicon controlled rectifiers, or SCRs. In this case, we've got a full wave bridge. In other words, we are rectifying both the negative side of the AC waveform as well as the positive side. And we're going to gate that on through the SCRs. So our gating signal out of our controls will tell the SCRs how much we want to gate how much of that AC waveform we're going to allow through, or we're going to rectify. And in this case, at 100% output, you can see at this first line that I'm taking both the positive side of the sinusoidal waveform as well as the negative side and fully gating it on. If I only need 50% of the output, I'm going to delay that gate of that AC wave of that SCR and only allow half of the AC waveform to go through. So that's an SCR based power stage. However, one of the advantages of many of our digital voltage regulators is we use a pulse width modulated power stage. So we'll talk a little bit about the advantages, but first let's just take a look at how it works. So rather than have the SCRs on that kind of that bridge input, like the full wave SCR based, we're just putting a diode based bridge here. This diode based bridge is turning the AC, rectifying it all into DC, and charging this capacitor. We call this the bulk capacitance. So it's basically just charging that capacitor to a full high DC output. And then we use an IGBT, or an integrated gate bipolar transistor, to create pulses out into the field. So based upon how much excitation we need, we're going to increase or decrease the pulse width and provide the DC to the exciter field. So at no load, you can see I have these little bitty pulses. If I'm at average load, I've got a little bit bigger pulse. That's this middle line here. And if I'm at full forcing, or I need a lot of DC into my field, I'm going to have a full gate. So basically, gating as much as I possibly can to provide excitation to the field. So the reasons why we use pulse width modulated power stages are many. There's some advantages to them. It allows us to use three-phase PMG power. One thing I didn't mention when we were talking about the SCR power stage is those SCRs, because they have to know when to gate on and off, they are tuned to the frequency of the power input. So they may be only able to handle 50 or 60 hertz, or maybe they're tuned, or they're set up to handle a 400 hertz PMG. So it does require maybe a different power stage topology. Not that they can't be used in those applications, they're just not as flexible. When we go to a PWM power stage, if you remember, we're rectifying whatever that power input is to a DC that we're storing in that bulk cap. So we don't really care too much about what that frequency of that power input is. So it gives us a lot more flexibility for our applications. CR-based power stage also may depend on zero crossing of the sinusoidal waveform to know when to gate on. So if we have noisy power input, a lot of harmonics, high SCR loading, things like that are causing a lot of noise on the AC input, they can cause false triggers. So our SCRs are firing at random times, can cause some instability issues. Again, because of the topology of the PWM power stage, we're not as likely to have any misoperations because of the noisy input, because again, we're just storing it as a DC in that bulk capacitor. Likewise with the frequency, we can handle a high frequency, or we can even handle a DC input if a customer wants to put a battery input into the power input rather than an AC waveform. It also gives us the opportunity for high field forcing. So if you think about that power stage that we just looked at, we're rectifying all the AC, and that capacitor has the ability, minus any losses, of course, it has the ability to charge that cap up to the peak voltage point. So it gives us a lot more overhead and gives us a lot more forcing in instances where we need a high forcing reaction to maybe heavy load currents or fault currents. So this next slide shows an overview of our voltage regulators, our DECS line of voltage regulators, and what their power stages are. So we have two that are on this list that are pulse width modulated, or they use that IGBT output, and then we have two that are SCR outputs. So in this case, if you look, and obviously at various currents levels, that's depending on your application, you may need higher or lower excitation levels, which is hence the difference between all the models. We have the DECS 250, which is a 15 amp power stage, pulse width modulated. Then we have our DECS 250N, which is an SCR based power stage. It is capable of 20 amps, but we add negative forcing. So in that SCR diagram I showed you before, we were only rectifying in the positive direction. We do have the capability to also do in a negative direction, which gives us some better responses upon load rejections and times when we need to pull excitation down in a very quick manner. So there are some applications for a negative forcing power stage, which I'm sure we'll cover in future seminars. We also have a DECS 150, which is a 7 amp power stage, capable of 10 amps at 55C, and it's a pulse width modulated device. And then for our higher excitation applications, we have our DECS 250E, and we're able to produce that product at multiple levels of excitation current, anywhere from 50 amps to 200 amps. And that one uses an SCR-based power stage. Okay, so there's kind of a little bit of background to how the voltage regulator works, but some of the advantages of digital voltage regulators is now we have a microprocessor in the unit, so we can do a lot more calculations and do a lot more cool things with the voltage regulator. Primarily, we have a lot of customers that are going to parallel generators. So when we parallel generators, it requires us to look at the current output because we need to be able to control, at a minimum, we need to look at bars and the amount of reactive loading that is on that particular machine. So the voltage regulator controls the reactive power out of the machine. The prime mover, which is the governor, which is controlled by the governor, controls the real power, or the kW, out of the machine. So obviously, talking about voltage regulators, we're mainly concerned with that reactive component that's being outputted out of the machine. So therefore, we also need to look at the current, which will allow us to parallel the voltage regulator, and we can run this in multiple modes. We can run it in voltage droop, we can run it in cross current compensation or reactive differential. We can do kVAR control, or we can monitor the phase angle and do power factor control, because now we have the capability, by looking at the difference in the phase angle between the voltage and the current on the output of the generator, to be able to calculate these different parameters and control them. There's multiple operating modes. The very basic is a manual control. Primarily, we're going to use field current regulation, or what we call FCR mode. So what that does is the voltage regulator doesn't care about the output. So at what I just told you about voltage and the voltage output of the machine and the current output of the machine, if I'm in FCR mode, the voltage regulator doesn't care. It is strictly regulating the field current, the amount of current it's putting into the exciter field. We can do this exact same operation, except rather than looking at current, we can do voltage, and that's called our FCR mode. So both of those are manual type control operations. These are good in situations when you're trying to troubleshoot, if you want to check your sensing configurations to make sure everything is correct, you have the proper phase rotations, things like that. So it's a very helpful tool, but not typically the mode you're going to operate in normally. So obviously, a voltage regulator, we want to be able to do automatic voltage regulation. So this is just saying that if I want my voltage or my generator to run at this voltage, I want to monitor it, control it. So again, like those block diagrams, the basics there. But again, since we're looking at current, now we can look at that reactive component. So That gives us the ability to do VAR control or VAR regulation mode. So now if I am tied to a utility or a very high source, bigger source, I should say, such as a utility or a much larger generator, I may want to run that machine at a particular VAR output. So I want to control the amount of reactive load that I'm outputting. I have to have a source that I'm paralleled against that is going to control voltage. So that's why when you're running in a VAR mode or a power factor mode, rule of thumb is 10 times bigger, but there's obviously some room around that. But I want a source that's going to regulate voltage. So in this case, this particular generator may not be able or should not be able to move, let's say, utility voltage around and unparalleled utility. So I can run in a VAR mode. So I can change my excitation levels, and I'm not going to change the voltage because the utility is regulating the voltage. So now I'm just changing the amount of load out of that particular machine. The same scenario is true for power factor regulation. I do not want to be able to change voltage with this particular machine. I just want to be able to change the VAR component out of that machine to change the phase angle between the reactive power and the real power. And that phase angle is ultimately power factor. So I can do power factor correction at a plant level or at my point of common coupling. And if I'm just paralleling multiple machines, I am going to want to make sure that they're sharing load correctly as they're parallel. So I want to make sure that each machine is doing its equal contribution to supply the reactive component to that particular load. So I can do this in multiple ways. We can do this in droop control, and we can do this in reactive cross-current compensation, or some people call it reactive differential compensation. That's just like tying all my CTs in a kind of a loop, which will end up balancing themselves out and make sure that each machine is sharing properly. And there's actually a third method in here, which we'll discuss a little bit later, which is a benefit of digital voltage regulators, is now I have the ability with the microprocessors, I have the ability to communicate from voltage regulator to voltage regulator. So I can share the reactive component just by communications, and we call that network load sharing. So one of the things that always comes up when we talk about digital voltage regulators is I have to set the gains. I have PID settings. So here's a slide with a lot of words on it. So I'll read the first part. Digital regulators implement stability response time control by executing complex instructions from program memory. So a lot of words that basically are saying now I have a microprocessor. So rather than using circuitry to do my stability response, I'm going to use numbers and gain settings, and my microprocessor is going to calculate based upon what I tell it how much output to give to make corrections to the voltage. And it does that by using three sets of gains. We use proportional gain, integral gain, and derivative gain. Proportional gain, I'm going to kind of describe this in the terms that I like to describe it in. But proportional gain, if you think about it is looking at the magnitude of the air signal. So I've got some gain setting and I've got so much air. If my air is very high, I'm going to multiply it times that gain setting, and that's how much output I'm going to give my voltage regulator is going to give to make a correction. So the further away I am from set point, the more output or the more gain I'm pushing out to drive my set point to zero. So what happens is, as I start to drive it, I'm hopefully correcting in the right direction. So my difference or my air signal keeps getting smaller and smaller and smaller and smaller. Well, as I get smaller and smaller, my output gets a little smaller and smaller and smaller as well. So by definition, proportional gain will never drive the voltage perfect. It's always going to have some type of error because the math just works that way. So I'm never going to be able to drive it all the way to zero, which is why we implement integral gain. So integral gain does takes a different look at it. It's saying, okay, I haven't got to zero yet, so I'm going to increase my output. I haven't got to zero, I'm going to increase my output. So it's continuing to give more to try to drive it to zero. So by definition, or by theory, PI is really all I need to be able to drive my air signal to zero. But we like to introduce also derivative gain. Derivative gain, I'm going to show my age here, but when I was in control classes back in my schooling days, it was also referred to as rate. And I kind of like that term a little bit better than derivative because it means a little bit more to me. But derivative gain looks at the rate of change. So it's looking at how fast I'm driving to zero or how slow I'm driving to zero. And it's going to change that amount of gain or the amount of output based upon how quickly I'm driving to zero. So at a high level, when I look at proportional is how fast I'm going. So it's my rate of change, how fast I'm driving there. Integral is my steady state stability. It's getting me to, it's after proportional has done the majority of the work, it's kind of getting me there to make sure I'm stable and I'm driving to zero. And derivative is almost looking into the future. So it's kind of looking at how fast I'm moving, and it's going to start correcting based upon the speed I'm going. So it can help with overshoots. So proportional is typically rise time, integral is steady state, derivative is overshoots. So that's kind of at a high level how those gains fit in. We go back to our block diagram. This is kind of calculating that error signal. So I've got my set point change and I've got my error signal, and now I'm taking that error signal and I'm multiplying it times each one of those gains to create the output that's going to drive my power stage. Here is a strip chart recording of a 5% step change. So it's just showing the reaction out of the machine and what our goals are and while we're tuning these things. Excuse me. So at the top is actually our generator output voltage, and at the bottom is showing the output of our voltage regulator. So you can see I'm going to do a step change. I'm going to ask for a reduction in voltage. Our field voltage drops down, and then as the voltage starts to collapse, then it starts to come back up to recover to give us a nice transition. So this is a very stable generator, very stable response. And then I'm going to step back up my 5%. We're going to see that output spike in the generator voltage, and then it kind of collapses down and creates that stable response. So the exciter field, what this is really showing is our exciter field reacts much quicker than the output of the generator. That's because of time constants. So that's what we're tuning to, the time constants of the exciter field and the generator field, which is why we need to change those based upon each particular machine. Time constants vary between different sizes of machine, different makes of machine, so on and so forth. So PIDs allow us to be very flexible and match our output based upon the reaction of the machine. So if anybody has ever tried to tune a voltage regulator or even tune any PID loop without knowing any of those time constants of that process or the generator or whatever, it can be kind of tedious. You have to kind of pick the gain settings and then make sure you get the right response, and maybe you're not happy with it. So it can be very time consuming, take a lot of trial and error. One of the features that Basler has implemented on our digital products, our digital voltage regulators, is an auto tuning function. So what we do is we conduct a series of small step responses. We'll basically input pulses out into the exciter field, and we'll look at the response of the machine. So the voltage regulator, by looking at the response of the machine, can internally calculate the time constant. So it knows when it put the output into the exciter field, and it looks at how the generator reacts. So we can calculate those gains automatically, and then we can always come back and fine tune it later. So those gains will get us a good response, a stable response, and then we can come back and just tweak those gains to get the response we want. Maybe it's too aggressive for our operators. Depending on the machine, they may not want the application, they may not want a very aggressive response. If I've got a lot of dynamic loads, I may want a very fast response that I can recover from those very quickly. So I may want almost, bordering unstable, where I get as fast a response as I can. So I can come back and retune and use those as my base settings to get me close. And now I'm just making little tweaks and not spending hours trying to get the right gain settings. While I'm doing this auto tuning function, the generator has to be running, and it needs to be spinning with no load. Of course, with the generator breaker open, and it has to be in AVR mode. Here's kind of a screenshot of our auto tuning function. basically what we would do is come in, we connect to the unit and start it during auto tune, and I can hit the basically start auto tune, and you can see here it's doing a few step responses, a little bump, looking at generator outputs, and then I do a large step response and then run through some cycling to make sure. And once it's complete, we'll come up with just a button that says auto tuning is complete, and then I can apply those gains. So it really is a simple process, basically a couple buttons pushed, and we should have stable gains on the output of our voltage regulator and generator. Okay, one of the other advantages we have with the microprocessor is we can add a lot of additional functions. If we look back at old analog systems, we'll say the more complex analog systems, we had a voltage regulator, and then we had a series of black boxes. So we may have had a over excitation limiter box, under excitation limiter, diode monitors, protective features, VAR power factor controllers. All those things were a separate black box in an older system. Now we're calculating all that. We have all the inputs into the digital voltage regulators, and we have a microprocessor which is capable, obviously, of doing all that math. So we can implement all these additional functions. So limiters are a prime example. So we can do an under excitation limiter, we can do over excitation limiter, we have a stator current limiter, we can do an output VAR limiter, which may be a little confusing for anybody that's familiar with limiters. Typically, an under excitation limiter is looking at reverse VARs or VARs flowing into the machine. The VAR limiter in a DECS is actually output VARs. It's limiting the total amount of VARs that are flowing out of the machine. So it works a little closer to maybe a stator current limit than an under excitation limiter. Both are looking at VARs. And then we have our under frequency or volts per hertz limiting. And we can also scale these based upon temperature. So we can do thermal scaling for our over excitation limiter over stator current limiter, which could allow us to maybe increase the output of that particular machine if my ambient temperatures are low enough to handle the heat dissipation. So here's a BESTCOMS screenshot of our under excitation limiter. So this is basically comparing the amount of reactive power that I can absorb in comparison to the output or the real power of that particular machine. So I'm creating a curve. So I'm basically adding the two parameters to make sure I'm within the capabilities of my generator. And this can be set up as a fixed curve, or we can do multiple points to get very custom curves. So the DECS allows up to 5 points to set the under excitation limit. Over excitation, it's looking at field output. So we're looking at field current. So this is to make sure the machine's not getting overexcited. So we have two different types. There is a summing point type and a takeover type limiter within the device. Takeover type is kind of more of an inverse type limiter, where a summing point, we're setting fixed delays. This particular diagram is showing more of a summing point over excitation limiter, where I have an instantaneous over limit. So I want to set a cap on how much current that I'm going to allow the DECS to output, and it's going to cap it at an instantaneous limit. And then it'll allow it to run there for a particular amount of time, and then I can pull it down to a medium limit after that time delay expires, and then pull it down to my continuous rating or my low over excitation limit. So I can do up to 3 steps. We can also set them up for online and offline limits. And then the third type of limiter is our SCL, or stator current limiter, which is really looking at the output of the generator. So it's looking at stator current, or the output current of the machine. So I can set a total limit of current to limit the amount of excitation, at least, that I can push out of that particular machine, to make sure I'm not damaging or overloading the machine. So that is what the stator current limit does. When I combine all of those limiters, so I combine all those limiters together, I can mimic, if properly set, I can mimic the generator steady state stability limit. So you may be familiar with the generator capability curve is another term for this, but the generator capability curve, which shows where that generator's operating range is to make sure that it's in a safe operating range and not in a damaging situation. So I can tune these limiters to make sure that the voltage regulator, at least, to make sure that it is not operating outside of the safe operating region of that particular machine. We also have an under frequency limiter and a volts per hertz limiter. They're very similar in functionality with a few differences. In this case, this is the under frequency limiter, where I set a corner frequency and a slope, basically. So what this is doing is it's setting a limit on how much output I can give at a particular frequency. So if my frequency is not at 100% or not at optimal operating range, I want to limit the amount of excitation or the amount of voltage I'm going to allow the machine to build to. So I'm really kind of taking my set point and backing it off. There's two reasons for this. One is if I'm running at a slow speed, that machine may not be designed to operate with excitation. It's designed and dissipate the amount of heat it needs to do. So we will operate at a reduced output in those conditions, so it allows the proper amount of airflow. Typically they're designed to run at their nominal frequencies. If I'm lower, I don't want to put a lot more heat into that machine and potentially damage it. The other thing it does is it can allow us to tune to load applications. So what happens in a machine as I add load onto it? Let's say I block load it. I put a large load on it, generator voltage drops, generator frequency can drop. As generator frequency starts to drop, now I need more excitation to make the same amount of voltage, because I'm at a slower speed. So voltage regulator will normally then just increase excitation with zero limiters. I'm going to increase excitation to try to get my voltage back up. Well, if my prime mover is already has this huge load on it, now I'm putting more excitation on it. I'm putting more flux on the rotor. Now I'm putting more electrical load that's inhibiting my prime mover from getting back up to speed. So I'm just putting more load on the machine when I'm trying to recover it. So that's why we add a volts per hertz limiter or a frequency limiter into the scenario. So now I have that initial load, my voltage drop, my frequency drops. Based upon that amount of frequency drop, I'm going to back off on my excitation and allow some time for my prime mover to recover. And we can tune this based upon our load. So we can tune our volts per hertz curve. So we have different sets of volts per hertz curves that can be used to get the response that we want out of the machine. So in this case, we have three different slope frequencies. We have a 0.66 per unit, a 1 per unit, and a 2.26 per unit volts per hertz curve. So at a 1.66, I'm not decreasing my excitation as much. And you can see at the bottom of that graph, this is one all the way to the left, my frequency drops pretty low. If I go to a 1 per unit, my frequency doesn't drop quite as much. And if I go to even a more aggressive slope of the 2.25 per unit, I have even less of a drop in my generator frequency. Now, it is also could be a trade-off. If we look at how quickly our voltage recovers, we have to tune that as well, because we may want to look at voltage recovery. So in this case, if you look at the top slopes, my voltage recovery on the 0.66 was pretty poor, actually, in both cases, voltage and frequency. But I can, as I change that slope, I can see the recovery. My voltage may dip more, but because my frequency is recovering quicker, in the case of the higher slope or the more aggressive slope, my voltage recovered quicker as well, basically because my frequency recovered quicker. Another one of those black boxes that were out in those systems were diode monitors. So brushless exciters have rotating diodes in them to get the to provide the excitation to the field through the exciter. So what happens is every time one of those diodes fire, basically they will produce a ripple current, which is reflected back into the exciter field. So what the voltage regulator can do is monitor that ripple current and determine the health of those diodes. Shorted diodes, they are easy to detect. They're going to create a pretty noticeable ripple current, so we can detect those much quicker. Open diodes can be a little trickier to detect. They don't quite get as much ripple current, so we have to be tuned. The detection has to be tuned correctly, and may take some additional time to detect, but it can be done just by monitoring our exciter field. And here's kind of a graph of the ripple currents out of an exciter field in different conditions. A is all normal, so we can see we've got normal, nice, balanced ripple current. B is an open diode, so we've got some normal ripple currents with one that's just open, and it's kind of letting we're just kind of missing a pulse there, I guess, but very much more difficult to detect than a shorted diode. You can see a shorted diode there is just really it's conducting basically, and it's showing a very large ripple compared to the very small ripples as seen in A or even B. Other DECS features, the DECS is able to sense three-phase current, where traditionally it's been single-phase current, and we also have a separate CT for cross-current compensation. That's to make sure that we're still able to meter as in cross-current compensation. The idea is that all the currents within all the CTs across machines will balance each other out and doesn't allow for proper metering, which also affects protection such as limiters and other things. So we have three-phase. We can get three-phase current inputs. We have programmable I/O to do whatever functions we need it to do. So we talked about diode monitoring. We can also have much better event recording, so we can know what happened in the system during normal operations or in particular in fault conditions. The real-time monitor is very useful during troubleshooting and tuning. We have programmable logic, so we have integrated PLCs basically. And as I talked, we were able to share over communications or reactive load sharing over Ethernet. And then also just communications back to SCADA systems or monitoring devices through Modbus RTU or Modbus TCP/IP. Excuse me. Here's just a diagram, some real-time analysis. So this is that real-time monitor. I also showed it during that step response, but this is integrated into our BESTCOMS software to allow a user without having to use external strip chart recorders. We can just look at the software and be able to do our tuning and monitor step responses. Very useful tool. Some of the other things we do in voltage control and the voltage controllers with digitals, we're able to do redundant systems or redundant functions. We do this through Autotracking. So with the single DECS unit, we have internal auto-tracking controls. So this allows the DECS to track mode to mode. So let's say I'm running in power factor mode. I can also have my VAR mode tracking or my AVR mode tracking or my manual mode tracking. This is very useful, especially in cases when I maybe have a loss of sensing configuration I want to transfer to manual. It allows me to keep that machine online in manual and bring it down safely rather than just tripping it off maybe under load. But sometimes we need more redundancy than that. So we can add dual systems. We can add whole second DECS. This allows, it was what we call external auto tracking, which allows a DECS to DECS communication. So we have a primary DECS, which is actually doing the work. And then we have the backup DECS, which through communications is monitoring what the primary DECS is doing. In the case of a fault with that primary DECS, then I can transfer to my secondary DECS. Again, keep that machine online until I have a regular maintenance cycle or need to take it down for other reasons. We also can do microprocessor watchdogs, voltage matching and auto synchronizing internally to the DECS, so we don't need a separate box for those things. Auto tuning, which we talked about. And in some cases, customers may need a power system stabilizer. So this will allow us to add a multiple setting group power system stabilizer. We can use different models um, depending on what the application is. So it is an option within our digital products. And again, since we're monitoring all the different parameters throughout the generator, we can add protective elements, not just what a voltage regulator is looking at, such as the field itself or the diodes or the things we've already talked about, but we can also do reverse power, over under voltage, over under frequency. Multiple other protective functions can be incorporated. And if there's something in the application that is not in the DECS as far as a protection function, we can do configurable protection. So this is a really useful tool that's integrated into our software. It allows you to look at basically any parameter that the DECS is monitoring, and you can set up thresholds or limits, and you can use these to do protective functions or control functions. So it's just a very configurable way and flexible way to add additional features into your excitation or into your voltage regulator system. And here's just a screenshot out of BESTCOMS showing that. So you'd select your parameter, tell it when it's going to be active, if we want to put some delay or hysteresis, and we can do up to 4 thresholds. Basler utilizes BESTCOMS Plus software for all of our digital products, all of our new digital products anyway. So the advantage there is if you're familiar with it from a protective relay function or a genset controller function or voltage regulator functions, if you see any of the other devices, you're already familiar with our BESTCOMS software. So it gives us a full metering. It's intuitive setup, especially once you're familiar with it. And again, we can do the event recording, oscillography, sequence of events. It has the fully programmable logic. It can allow for remote I/O configurations if they're available for that particular product, and again, our auto tuning. From a metering standpoint, we have the digital products will meter pretty much anything we're looking at from the regulator, or anything that we can calculate. So on the bus, if we have a bus input, we can look at the sync angle, slip frequency, obviously to do our synchronizing. Bus voltage, bus frequency, and the generator, we have obviously voltage, frequency, power factor. We can also do some internal things from like a tracking error or output, the control output, or the amount of output we're putting out into the field, set point position indicators, so on and so forth there. Control panel. This will pop up in the metering screen of BESTCOMS. So remotely, I'll be able to do start, stop. I can change modes of operation. I can control virtual switches, breakers to do other things as I tie them into logic. Gives me a status indication of what modes I'm in, if I want to raise or lower set points. All of that done from the BESTCOMS Plus software. You can set up alarms. We can set those up for basically disabled alarms, or we can set up for latching or non-latching alarms. So latching alarms, once they happen, they're going to stay there until they're reset. A non-latching alarm will just be present when that condition is present. And here's our PLC, our programmable logic. So this is all drag and drop. It allows you to take inputs, outputs, elements, control functions, and we drop them in there. And we can tie them to outputs, we can tie them to other elements or functions, and it is as simple as taking your mouse and clicking on one point and pulling it and drawing it to another point. So it's very easy to use, very simple and very flexible. Another screenshot of BESTCOMS Plus, showing some of the components, and we have and or exclusive ors, a lot of flexibility there. And for certain applications, we may need some accessories. So the DECS, for instance, the DECS 250 is set up to be rear panel mounted, but we also have a front panel mounting bracket. Can do very similar things for other devices. We can add on interactive display modules or remote display panels, additional contact expansion modules or analog expansion modules, so just to add more flexibility into the system itself. So multiple accessories available. They meet full environmental requirements. So I think we have some of the highest in the industry at -40 to +70 degrees C operating. Our products are rugged, well built, 5 Gs of vibe, 30 Gs of shock. All the environmental testing that we do to make sure that it's a reliable product. And based on the product, we have multiple agency requirements. I think every one of them is UL and CSA, or CUL, US, CE, and then we have multiple marine agencies as well that are available. As far as ordering, some options are style ordered, so not everything is available in every particular unit. In the case of the DECS, I think the big one is a 1 or 5 amp secondary input for the CTs. The PSS is an option in all of our models. And then your mounting configurations and how you want to set it up. So the style chart walks you through to make sure that the product you get is, meets your application and your intentions for use. 250 is very similar. 250 utilizes you have an external power supply, so we have to select that at either a 24 volt or a 125 volt power supply. So with that, I appreciate everyone for your time, and have a good rest of your day.